Hello everyone, my name is Juan Camilo Osorio. I'm a PhD student from the Program of Structures Lab at Purdue University, and today I'm going to present you my research entitled Effect of Boundary Conditions on Multistability of Tape Springs, directed by Dr. Andres Arrieta. Tape springs are characterized by being multistable structures based on prestress along their thickness, which give them two possible energy states with two different prestress configurations, as you can see in the figure. Apart from being really fun toys, these structures have been utilized in aircraft and deployable structures where they are combined together to form multistable structures like the one developed by Santer and Pellegrino, where they link different tape springs and generate a multistable adaptive structure with the state shown in the figure above. Also, in the work developed by Gatto, a tape spring was added to the wingtip to improve the aerodynamic capabilities and behavior of the whole structure and wing. Despite its potential, one of the key issues is the integrability between the bistable element and the complete structure, as in many cases it forces the element to lose its morphing capabilities, and it's not desirable. This integrability can be examined throughout the boundary conditions imposed in the bistable element and the effect it has in the structure. There have been different works regarding this issue, where bistable structures are achieved with different boundary conditions. For example, fixed boundary condition with multi-section composites, developed by one of the members of our group and Dr. Arrieta. Also, Brunetti studied the effect of the initial shape of the shell in the bistable configurations as they are fixed in one end. So essentially, the curvature of this edge when you clamp it. He generates these bistable maps where they show that there is a relation between the initial radius of curvatures in the section that is going to be clamped and the bistable behavior. Despite this and many other works being able to produce and study this type of bistable elements, in our knowledge there is not much information about the real effect of the boundary conditions in the bistable element, and there is not a criteria to determine if your element will be bistable or not before you clamp it, just based on geometry and prestress. To address this issue, this presentation would have the following content. First, we'll address the methodology used, how we calculate the prestress of our tape springs, analytical formulation to determine the stable states, the FEM comparison with analytical model to ensure our model is satisfactory, and some results regarding the bistability maps and how it losses with the boundary condition. Then an analysis regarding the bistability loss, why it happens, and finally some conclusions and future work. So for the methodology, we start with our material properties. Here we select beryllium copper with a thickness of 0.1 mm, and we will need all this stress strain curve, including the elastic and the plastic part, as you can see here. This in order to calculate the plastic prestress for the tape spring that will fit our analytical model, joining our boundary conditions that we want to fulfill. Now, for this, we compare it with the FEM analysis to ensure our results, and then we're able to generate our bistability maps with two different conditions, the free boundary condition and the fixed free boundary condition. With this information, we can analyze why the bistability is lost, also using the FEM analysis, as this gives us more information about what's happening inside the structure. Finally, we came up with a criteria to maximize the possible bistable configuration after you clamp this type of elements. Okay, to calculate the prestress, you use a bending process already published in literature, where we start with a flat plate and we first bend it plastically in one axis. You can see here the stress along the thickness. Then you release it and let it recover its elastic part. This is called the spring back. Then you flatten it. Always consider that this flatten needs always to be elastic. Then you curve it in the other direction, generating plastic deformation in the other axis, and then you release it again to get the other spring back. Theoretically, these two spring backs will be your stable states. However, they recommend that after you achieve this spring back, you flatten again the plate and release it to really know the other stable state. To model this, we use two plastic models, the isotropic hardening and the kinematic hardening. Here I'm going to explain how it works with the equivalent stress strain curve and geolocus plot, which essentially give us every point inside the red dot line is elastic and every point outside is plastic. So here we start with the first plastic deformation. We achieve this stress and we exit the geolocus. Then this isotropic hardening change our gel stress and increase the geolocus. And then we go to predict the spring back, which essentially is trying to determine the stress profile that gives us one of these moments to be zero, depending on the axis you bend. So then you predict the spring back, so you remove the load and you get this point, and then you flatten it, considering that you need to be inside the geolocus or in the elastic part. Then you deform it again. Here you can see that the isotropic hardening doesn't actuate that much, but the kinematic hardening moves the geolocus from one position to another. After this, you again predict the spring back. You end up in the E point, and then you add the two extra steps that I was telling you in the previous slide, where you flatten the plate and then you plastically deform it. Theoretically, the two stable states would be E and G. And this is because all this available strain energy under the strain stress curve. After we got this pre-stress, we can then construct our analytical model. We use the Rayleigh-Ritz method, where we introduce the pre-stress as this force and moment vector, and we approximate the strain and the curvatures using polynomial functions. And we did this for two different cases. The first one, all free boundary conditions with 14 degrees of freedom, and the second one, a fixed free boundary condition with 22 degrees of freedom. As this particular case is quite complicated to predict curvature, what we did was divide this in two sections with continuity boundary conditions in order to predict more complex curvatures. In order to ensure our analytical model was adequate, we compared this to FE simulations. Here you have the analytical model and the FE, and a comparison in the middle section of the shell. You can see that the root mean square error between the analytic and the FEM simulations are quite close, which indicates that our analytical model is quite accurate. We did the same for the fixed free boundary conditions, where here we are able to predict the out-of-plane displacement of the most difficult state, which is this one, and we can match more or less the shape of the out-of-plane displacement in this region. However, we get excellent root mean square errors, and we're able to predict the two stable states quite accurately. So as that our model works, we proceed to construct the bistability maps. Here is for the free boundary conditions. So essentially, the black dots represent bistable configurations, and the white regions is monostable configurations. The y and x axis are the bending radius for the pre-stress. So essentially, it's pre-stress. And you can see that as you increase the aspect ratio, you are getting more bistable configurations. This is just because as you make the structure bigger or the element bigger, you'll induce more energy into the system, and some stable state will appear. In contrast, if we make the fixed frame, so here we make a comparison plot where the gray points are essentially the same as the previous slide with the free boundary condition, and the black dots are the bistable states with the fixed boundary condition. So as you can see, as you increase the aspect ratio, you start regaining that bistable behavior. This led us to believe that that the effect of the boundary condition is a function of the total length of the shell, and we need to examine what's happening when you reduce too much the total length. To do this, we use FE, and we use a shell with an aspect ratio of 2 and this pre-stress. And what we did was examine when you have a free boundary condition, and then you compute what's happening. So when the structure is totally monostable, you will get this stable state, but when it's BSL, we will get this too. So essentially the most difficult state will be this one. So we focus more on this state, and we analyze the moment in the y-axis as it is the one responsible to make this state snap to this one. What we found here is that the fixed boundary generates a boundary layer that interacts with the free boundary. This free boundary is the one, for example, that generates anticlastic behavior in the free configuration and tries to snap the structure to the other configuration. So there's an interaction between both boundaries, and this might be the cause of the element to be bistable or not. So we decide to examine these two boundaries by separate. So first one, the free boundary condition, where we see in the FEM results that the edge moment in the free edge decreases to a constant value in an exponential way. Actually, this corresponds to what we found in literature, that every edge load decays with a decay rate depending on different material properties. For this case, when you are totally free, you can calculate this decay rate from the homogeneous solution of the equation of the shell, in this case the cylindrical shell, and it's a function of the Poisson ratio, the thickness, and the prestress applied. Okay, now for the fixed boundary condition, what we did was analyze it with FV first, where we start with an initial curvature equal to the one in the free, generated by the prestress in the free configuration, and then we clamp it. Here we can see the boundary layer clearly, and if we trace a plot in the middle section, we can see how this stress decays in an exponential way until it becomes constant. So you can basically calculate this decay with these expressions. However, in this case, as it is called the Sandband effect, which states the effect of an edge load throughout the domain, this is just dependent on the type of material you're using, so essentially isotropic, orthotropic, or anisotropic, and the width of the element, which is this dimension. So you can calculate this by solving the compatibility equation and supposing an area stress function with an exponential term. So we came up with this criteria. So the idea is that these two boundaries doesn't interact, and we need to solve these two boundary equations. So here epsilon is the percentage of your you want your edge load to decay. So essentially, if this is 10%, is the amount is that the edge load decays 90% at a distance of d. The same for this one, and we want to verify that for a bistable free element to retain its bistability, both boundary layers must not interact. So essentially is that the sum of these two parameters cannot exceed L, the total length of the shell. So we can calculate these decay rates by solving the equations. Here you have for the free boundary conditions, where it's dependent on the thickness of the prestress, which is essentially this geometric parameter, and in the Poisson ratio. Now, in contrast, for the Sandband effect, it's just a function of the width, or Ly, and of a parameter eta that depends on the material properties. For this case, for this isotropic material, will be around 2.1. And so we came up with this inequality that if it is satisfied, you will get bistable behavior when you clamp your element. To test this, we use the prestress. We have been working to analyze all this, and we solved this equation where we found that we need an aspect ratio of 1.3, and you can see that if we just reduce the aspect ratio by 0.05, the structure is not able to hold the higher energy stable state and will snap to the lower energy one. As you can see here, it stays in this configuration, and this one just stays. So essentially, it's a good criteria to determine whether or not your element will be bistable or not. To conclude our work, first, the prestress using plastic deformation was successfully utilized to produce bistable structures. Analytical model shows that bistability loss is a function of the length due to the interaction between boundary layers, and this can be calculated using the Sandband effect and the free boundary layer solution. For our future work, we'll need to determine the importance of epsilon and the dependence of the prestress and the edge moment required to clamp the structure in this parameter, as we have discovered that it has a huge impact. And also we could test more boundary conditions. For example, one of the most popular ones for this type of element, that is fixed boundary conditions.